according to the theory of evolution, the origin and development of the universe and all its systems can be explained solely on the basis of time, chance, and continuing processes. All living things have arisen from a single-celled organism. A second and opposing worldview is the concept of creation. According to the theory of creation, everything in the universe has come into being through the design, purpose, and deliberate acts of a supernatural creator. That means this creator created the universe, the earth, and all life on earth, including all types of plants and animals, as well as humans. On today's edition of Origins, mutations prove creation.
Hello my friends, welcome to Origins. My name is Don Chapman. It's my privilege to be your host. Origins is a forum where we take the evidence of science and we use it to confirm the truth of creation. Usually we do that by bringing you some great guests, and we have one with us today. His name is Dr. Jerry Bergman. Dr. Jerry, we've talked about your degrees in other shows, but a lot of your work has been in the area of research, hasn't it?
Right.
And today we're talking about mutations, which ties in the whole exciting scientific study of DNA with this whole business of evolution, because this is where the mutations would have to take place for evolution to happen.
Right. The basis of evolution is clearly mutations. So that's the foundation for the theory.
And mutations have to take place in the DNA chain.
Right. That's the source of the material which natural selection selects from, is mutation. That's the ultimate source.
Okay. Now, today we're going to, we've got on the screen there, mutations prove creation. What does that mean? Why do you say that?
Well, because when we study mutations, we find, and I looked at quite a few mutations, and the question is, are beneficial mutations common? That's because of course, since evolution is based on mutations, are there many of them? Are they common?
And it would take positive mutation, not negative mutation, for life to advance that way.
Right. What they call beneficial or favorable. They sometimes use the term favorable.
Okay.
So I did a literature research. I looked at the scientific literature, and this is what I found. And I found a total of 170,000 mutations in a database called Biological Abstracts. And I found in Medline, another database, 283,205 mutations. This is all mutations, period. Of those that were beneficial, I found 98 in Biological Abstracts, 88 in Medline, a total of 186 beneficial mutations I located in the literature.
Out of almost 500,000.
Right.
Okay.
Now, some of these were articles that talked about the same mutation, so it's actually not a total of 186 beneficial mutations.
Oh, those are just articles.
Those are just articles, and they many talked about the same mutations.
Okay.
And there's some overlap between Biological Abstracts and Medline. They abstract some of the same journals. So this information isn't quite correct, but it gives you an idea of the small percent of the mutations described in the literature, the small percent that are beneficial, which turns out to be about 0.04%, which is considerably less than 1% of the mutations that's described in the literature were beneficial.
That's amazing.
So it's a very, very, very small number,
tiny
as you can
amount.
see. And of course, as we do more research, this will undoubtedly change. But my guess is it's not going to change too much one way or the other.
It's probably not going to go up, is it?
I doubt it. If it does, if it goes up, it may go up slightly, but that's all. And some examples of beneficial mutations. And I'm in the process now of looking at these, trying to find out, what mutations occurred, what changes occurred to make them beneficial. And I found that many were beneficial only for humans. They were not beneficial for the plant or the animal. And the best example is seedless fruit. That's a result of mutation, which is convenient for us. We can eat our watermelon without having to worry about seeds, or our grapefruit without having to worry about seeds. But it's certainly not beneficial for the, in this case, the plant.
So even when we're talking about beneficial mutations, we have to say beneficial for whom?
For whom, right.
That's right.
An important consideration.
And by the way, I love seedless watermelons. I think that's the way to go.
Yeah, well, it's...
Unless you're sitting in the yard, then it's all right to spit, but not at the table. So this is a really good deal for us. But if I were a watermelon or a grapefruit, I wouldn't be excited about not having any successors coming because I had no seeds.
Yeah, reproduction is a little problem for these, for these plants. That's true. And another example is they found in what they call Belgian blue cattle. There's a muscle mutation which produces beef which is more valuable to farmers because they end up with more muscle, they end up with more meat, they end up with more profit. So it's clearly beneficial to the farmer, and they're also low in fat. So it's tender, it's low in fat, so it's ideal for the farmer.
So even when we're talking about mutations being beneficial, depends on who, what point of view you're looking at.
Right, if we're the cattle in this case, or you're the farmer. And now let's look at the cattle. Well, the side effects for the cattle include a reduction of the animal's fertility. So it's not as fertile. So from the cattle standpoint, it's certainly not, again, a beneficial mutation. And another example, this is my favorite because I did a whole article on this. In 1791, Seth Wright discovered one of the sheep in his flock had really short legs. It resembled actually a dachshund. And he thought, now wait a minute, these sheep don't jump very high. They don't jump fences. So I can save money by having very low cost, low fences, and they won't jump the fences. Boy, this is an ideal mutation for a sheep herder because it save a lot of money. And as far as they could see, the meat was just as good, the fur was just as good, the wool. So they thought, gee, this is great. But what they found was that this is actually a lethal deformity which is called achondroplasia. And this is a normal sheep, but the mutation basically caused the legs to be not this long but much, much shorter. So as a result, it just looked like a normal sheep with very short legs.
And I'm reading ahead of you there, but that led finally to the extinction of that species of sheep. Which when you put that into the whole evolutionary thing, again, the mutations produce elimination. They don't produce a stronger, moving up the scale species.
Right. It was a mutation basically in the cartilage production. So the cartilage was deficient. So as a result, the cartilage, not only in the legs were a problem, but the cartilage elsewhere in the body were a problem. And they took a lot of these and did autopsies on them and studied them. In fact, there are a number of journal articles where they autopsied and carefully studied these sheep, and they found they had a lot of structural defects. So it was a major mutation. So we can see it's not indeed a beneficial result, it was a negative result. And it's interesting, this example was one of the prime examples Darwinists used to prove what they called mega mutations, which you have one mutation and you have a whole new breed. Because they actually called this a breed. It was called the Ancon breed of sheep. And they thought, well, gee, if we can get this whole new breed with one mutation, maybe we can get a drastic change in life with one mutation. We can have a mega step forward in evolution. And Darwin talked about this. Many of his contemporaries talked about this. So this was an exciting step that Darwin saw in evolution. Of course, it turned out to be total.
It's a step backwards, not a step forwards.
Totally a step backwards, right. Exactly what happened. And another example, this is an example of a beneficial mutation which is talked about a lot today in the literature. And this is a mutation which causes bacteria to be resistant to antibiotics. And this is a good illustration of what happens, how bacteria become resistant to antibiotics. What happens here is in the ribosome, and the ribosome is a structure inside of the cell. And the ribosome, this is the normal, picturing the normal structure. And a mutation basically prevents this normal fit. This is streptomycin. Streptomycin fits in here, and as a result, we can see it blocks what this section here does. So it's like a key in a lock. If the key fits, you can get in the door. If the key doesn't fit, you can't get in the door. So in order for streptomycin to work, the key has to fit. That's how it works, by the fit here. Well, a mutation, you can see, causes a little notch here because the shape now of the protein is different. So as a result, the streptomycin doesn't fit. So as a result, this bacteria now is resistant against streptomycin. It no longer is killed by streptomycin. So this bacteria clearly has an advantage in an environment with streptomycin. The problem is, though, in the wild, this does not have an advantage. It has a clear disadvantage. And the example I use in my class is that you go through a divorce and your husband has a key to the house and he can get in and take your things. How do you keep him out? Well, you change the locks, but of course can't do that here.
Right.
So the illustration here is you put some gum inside the locks.
Okay.
And he can't get in the house anymore. So you kept your husband out. The problem is you can't get in either. So it achieves the goal of keeping him out, but it also prevents you from getting in. But on the other hand, if you have a back door and maybe another key for that, you can still use the house. Well, likewise, the bacteria, they can still survive in spite of this mutation. But in an environment where you have streptomycin, they have a clear advantage. But they don't have an advantage in the wild.
So it isn't making it stronger or better, it just makes it resistant to that one thing.
Right, and
Okay.
in an environment which has the antibiotic. And when the patient goes home, even if they have resistant bacteria, sometimes back in the normal environment where they have the resistant bacteria compete with the normal bacteria, the resistant bacteria often cannot compete and they often die out. And that's called a fitness cost. And
Fitness cost.
fitness cost. And all mutations that I know of in bacteria which confer resistance against an antibiotic have a fitness cost. And there are many other examples. And one which I think is really fascinating is bacteria have pumps, where the pump basically pumps out of the bacteria, it pumps out the antibiotic. So you're giving antibiotics to the patient, it's being taken in by the bacteria, and the bacteria is pumping it out.
Huh.
Well, every now and then you have a bacteria that has a broken pump. Except it being broken so it doesn't work because those bacteria would die, it's broken so it's on high. It's kind of jammed in high gear. It's kind of like you put your accelerator on your car to the floor and it's jammed. So your engine is running in high speed and you can't stop it. Well, that's what happens here. So what happens is when these pumps are jammed on high, it pumps this stuff out really, really quick. And therefore, it has some resistance against the antibiotic. But in a normal environment, this pump is jammed on high, it uses too much energy, and as a result, that bacteria does not have an advantage in a normal antibiotic-free environment. So again, it's beneficial only in a situation where you have the antibiotic. It's not beneficial in a normal antibiotic-free environment.
So would it be fair to say, before you jump to the next example, would it be fair to say that the positive mutations are just adaptive, but they are not progressive?
Right. They're adaptive in a very limited situation.
But
and
they are not moving it on to become something bigger or better.
Right. They're not, as they call these superbacteria, but they're not. They're not more evolved bacteria.
Yeah, that's interesting.
And the last example I'll use is resistance to AIDS virus. And this is the AIDS virus here. And the AIDS virus, to get in the cell, has to have, in essence, two keys. Again, the lock and the key example. And the keys are basically receptors. The CD4 is one and the CCR5 is another. And to get in, they've got to have the keys to both of those receptors. Well, the AIDS virus has that. But now there are some cases where you have a mutation where this receptor here, and this receptor is made inside of the cell and is brought up to the membrane and then installed in the membrane. These receptors are damaged because of mutation. Therefore, this receptor is partially constructed. It never makes it to the surface. Therefore, this bacteria doesn't have the other receptor. Therefore, the AIDS virus cannot get into the cell. Therefore, this patient is largely resistant to the AIDS virus. They can be exposed to lots of AIDS virus, and they do just fine. They have no problem. But they are not evolving. These people are not more evolved. They have damage which this receptor doesn't work, and as a result, they have an advantage in a situation where they have the HIV virus. In another situation, keep in mind, this receptor doesn't work. So what this receptor doesn't take place because it's broken. And therefore, it has, again, a fitness cost in a normal environment.
So we're just not seeing mutations move us towards becoming stronger within a species, much less move from species to species.
Right. What evolution would require is evolving a whole new receptor, which is a new structure which functions to keep the HIV out. In that case, then it would be evolving forward, which is what Darwinism requires. But we don't see that, at least in all the examples that I've looked at, we don't see that. Now, I'm not saying examples don't exist. Certainly in the millions of mutations that exist, there's bound to be one that's clearly beneficial. I'm not saying they don't exist. I'm saying they're really extremely rare.
Very, very, very rare. Have you seen one in all your study?
I've never seen one in my work, no.
All of your study the mutation has either been negative, which leads to the death, or it's been adaptive but not really progressive.
Right. If I discovered one, I would be very rich and famous.
Well, if there's one out there, I hope you discover it.
Yeah, I'd sure like to.
But with evolution, we're playing a numbers game, aren't we?
Right.
And so, so we're going to talk about the number of mutations required for Darwin's theory to work. But before we do that, we've got to take a break. So don't you go away. You come back. We're going to see if this is possible in any realm. I'm going to give you a hint. It isn't. But you come back and be with us anyhow.
Creation versus evolution. You weigh the evidence. Skunk cabbage. Amazing abilities. The skunk cabbage is a uniquely designed plant which also has a built-in thermostat. If the air temperature drops as low as 10 degrees Fahrenheit, the skunk cabbage produces the heat it needs to maintain a temperature between 72 and 74 degrees. If the flower becomes too warm, heat is removed. Because of its amazing abilities, it is the first plant to break through the snow in early spring. How could this intricately designed flower be the result of random chance processes? Today's guest on Origins, Dr. Jerry Bergman, has been a featured speaker on many college campuses and at professional meetings throughout the United States and Europe. His research has been featured in many publications across the world. Dr. Bergman is also a professor at Northwest State Community College in the state of Ohio, where he has taught biochemistry, anthropology, geology, and microbiology. For more information about our guest, you can write to Dr. Jerry Bergman, Northwest State Community College, 22600 State Route 34, Archbold, Ohio, 43502.
Hi, we're back with Dr. Jerry Bergman. We're talking about mutations, and we're talking about positive mutations. We're finding out that word positive is relative to from whose perspective you're looking at it, if I'm right. Before we go to the number of mutations required, let's go back to this HIV cell and talk about how it becomes resistant. We'll use the DNA model over here and show us how does that happen.
Yeah, basically, in the case of the resistance to HIV, a receptor is not formed properly. And the reason it's not formed properly is because this code here, this is the code that produces the protein. One of the letters on this code is changed. We have a different letter. And as a result, the protein code, the chain which is produced, is not produced properly. So as a result, it doesn't fold properly because you have the wrong letter in there. So because it doesn't fold properly, it doesn't work. And that means when it's carried to the cell membrane to be put in the cell membrane to work as a receptor, it doesn't work because it's defective. It would be like in typing a sentence if you misspell a word. It doesn't make sense beyond that point. Now, we can often read words that are misspelled. We can figure out what it's supposed to say. But in this case, it can't. If you have the wrong letter in there, and that letter produces a code which doesn't fold properly, doesn't result in proper folding, it's not going to work. And as a result, that receptor does not function. And if that receptor is not there, that HIV virus cannot get into the cell. It's like to get into a house, you have to have two keys. The HIV to get into the cell, it's got to have both keys that both have to fit. In this case, the virus is okay. The receptor, the lock, key in a lock example again, the lock is broken, it doesn't work, therefore the HIV virus can't get into the cell. Therefore it cannot infect the patient, therefore the patient cannot get AIDS.
But that isn't making it a better cell, it's really a deformity.
Right, it's a deformity, and of course it's not an advantage except in this one particular situation.
So it's not really a positive mutation. I mean, it's a positive thing that it's resistant to HIV, but it's not positive in the sense that it's making it a stronger, better cell. Is that right?
Right. It's positive in a very limited situation.
That's right.
But assuming now we do have a positive mutation, we'll call it a positive mutation.
We haven't found one yet, but if you find one, let's assume we did. Okay. Now let's talk about the numbers. Okay.
So how many do we need? And now this again is estimating. People are guesstimating actually, but some people have tried to guesstimate how many we need. And one person estimated about 1,000 to 2,000 different proteins are used in our body, okay?
This is just the human body.
The human body. Okay. So we have 1,000 to 2,000 proteins. Different proteins are used. Now some of these are very similar. They're different forms of the same protein type. But we'll assume, for the sake of argument, we'll assume we've got 1,000. Okay, and these are all produced by the 35,000 human genes that Darwinism teaches evolved from other, less complex, often smaller genes. Okay? So we've got 1,000 to 2,000 different proteins. We've got 35,000 genes. So basically what we have to do is evolve these 35,000 human genes. Now, what's the likelihood of doing that? How many mutations do we need? Well, Shermer, he estimates that trillions of distinct modifications, i.e. mutations, were required to evolve humans alone. Now, Shermer, by the way, is an atheist. He's not a Christian. He's not a believer. So he estimates that trillions are required. And clearly, billions are required. How many billions, we don't know, but he estimates trillions are required. Each modification, then, probably would require many mutations, because we can get a mutation which produces a beneficial change. Then we get another mutation which goes backward. So to get the set of mutations we need, we have to have many more mutations than is required, because it's like going 2 feet up and 1 foot down. We progress and then we go backward, and we don't end up in the same position, but we still go backward. Okay? The fact is, though, beneficial mutations are very rare and virtually always carry a fitness cost, as we talked about earlier. So they're rare, number one. So how many, if we need trillions required to evolve us, how many do we need, period? We need many, 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 many trillions of mutations. And so I conclude from this, okay, that other mechanisms, even though they've been proposed, at its core, macroevolution requires new information. And the ultimate source of new information is mutations. And my conclusion is mutations simply cannot provide the source of genetic variation we need. And looking at that from many angles, we see we just don't get what we need to produce what we have.
So, does the word impossible come into play here, Dr. Jerry?
I would say the best word that describes the situation right is it's realistically impossible.
It becomes statistically impossible for this to work.
Right. Now, Darwinists say, yes, it's improbable, but we're here.
Yes.
We can't use a God explanation, because that's theology. We can't resort to that explanation. So, yes, it's highly improbable, but improbable things happen. Here we are. We know we're here.
So it only becomes likely when it's like saying, we know the answer's over here, but we're not going to look over there. So as long as we're looking over here, we have to assume this to be true.
Right. They assume this is true in spite of the evidence.
Because they've already eliminated God as a possibility.
Right.
So who's being objective here? It seems to me that if you're saying God could have made this or it could have evolved, you're going to very obviously quickly come to the point where you're going to say God made it, because the other side is improbable to the point of impossible.
Right. They say the rules of science are such that you cannot appeal to God. That's what they say. But my question is, who made those rules up?
Yeah, they made the rules.
And don't those rules limit? Why limit explanations?
You know, it seems to me, whenever I hear the term mutation, it takes me from the front page of the paper that's talking about facts and history and what's going on in current events in the world to the comic page. I mean, when I enter the realm of science fiction and I begin to pretend that we can have a Spider-Man and a Ninja Turtle and a Superman because these things have happened, that's fun for the comic page. But when we enter the world of reality, mutations simply do not make us better.
Right.
And so it seems to me that this is all a fairy tale. It's science fiction. It's not science. And I think that is the point that we come to. We cannot eliminate God. God is there, and God has made us.
Right.
My friend, I just want to wrap this up today by talking to you about the fact that it's God's view that He made you. That's what we say at the end of every show. And the people who are coming up with these theories are people who have said, we must eliminate the truth so that we can look for other answers. I don't believe you're in that camp. I believe that you're a person who will look around, and as the Scriptures say, that creation declares the glory of God. And as long as you intuitively know that, I believe you're searching for truth with us. My friends, I want to tell you, God has made us, and the evidence is overwhelming. And now we're beginning to see that the evidence of science refutes, doesn't confirm, it refutes the theory of evolution. And so I just want to remind you as we leave today, I want to thank Dr. Jerry. It's been a great show.
Thank you.
You've given us awesome evidence. But I just want to remind our viewers as we go today that it's still God's view that He created you. And that should be your worldview too. Till next time, God bless you, and I hope to see you again.
Thank you for watching this edition of Origins. If you'd like a copy of the PowerPoint information presented today, you can download a PDF file of program number 507 from our website at www.originstv.org. Or for a DVD of this series, send a $12 donation to cover shipping and handling and write to Origins program number 507, Cornerstone Television, Wall, Pennsylvania 15148.
Origins is made possible by the faithful prayers and the financial support of you, our Cornerstone Television family.